Welcome to this explainer. Today we are mapping out the absolute ultimate blueprint for how to design back-end APIs. We're going to trace this entire journey together, starting way up high with broad architectural choices and diving all the way down to ground-level execution. So whether you're laying the foundation for a weekend project or you're architecting a massive system meant to serve millions of users, this explainer is your blueprint. Let's get started.
Let's actually kick things off with a quote that's often referred to as the fundamental theorem of software engineering. Butler Lamson famously said, "We can solve any problem by introducing an extra level of indirection." And honestly, that is exactly what APIs are. They're the ultimate abstraction layer. They allow completely different systems, different teams, and different tech stacks to just seamlessly communicate without anyone needing to understand the complex, messy machinery under the hood of the other components. So here's our roadmap for today. 1. The back-end API landscape. 2. Crafting efficient, RESTful APIs. 3. The power of idempotency. 4. Scaling with microservice architecture. And finally, 5. Security and abstraction layers.
Section 1. The back-end API landscape. Setting the foundation.
You know, before any system can scale up to handle massive traffic, it almost always starts right here, the classic single-server setup. If you follow the request flow, a user hits the DNS, which routes them directly to our single web server to fetch their data. It's incredibly simple, right? Your web app, your database, your cache, they are all just living together on this one single machine. But as your traffic grows, you very quickly have to make some tough decisions about how to structure all that data flowing through the connection.
And that brings us to our first major fork in the road, choosing between REST and GraphQL. Now, REST is the traditional approach. It gives you simple, consistent contracts with very fixed endpoints. It's fantastic when you just want pure predictability. GraphQL, on the other hand, which was initially developed by Meta, represents a totally different philosophy. It's a query language that actually shifts the power over to the client side. It's highly flexible, meaning the client can specify exactly the data it needs and nothing more. That makes it an amazing fit for really complex or rapidly changing front-end requirements. But a quick warning, that flexibility definitely comes with a steeper learning curve, and it can allow for some pretty abusive queries if you don't safeguard it properly.
To really understand GraphQL, you have to look at the mechanical difference. A GraphQL server basically acts as a really smart middleman, sitting right between the client and your backend services. Instead of making 3 completely separate requests to, say, a user service, an order service, and a product service, which is exactly what you typically do in REST, the client just sends one single query. The GraphQL server does the heavy lifting, aggregates those multiple underlying requests, and hands back one perfectly optimized response. It completely prevents overfetching data you don't need and underfetching data that forces you to make annoying follow-up requests.
Section 2. Crafting efficient RESTful APIs, simplicity and predictability.
Look, GraphQL is incredibly powerful. But let's be real, REST is still literally the backbone of the web. When you're crafting a RESTful API, you want to build on a rock-solid foundation of predictability. First, your design needs to be domain model-driven. That just means your path structure should logically reflect your actual data models, things like users, orders, and items. Second, use semantic paths. Always use singular and plural nouns like /users or /orders instead of verbs. And third, use proper HTTP status codes. Define a limited, highly predictable number of status codes. Keep it simple for the developers who actually have to consume your API.
When we expand on those basics, a few really specific pro tips stand out. For example, versioning. Baking your version number into the path right from the start, like /v1/users, is a real game changer. It makes future upgrades completely painless. Also, think about bulk operations. They become so much easier if you support batch processing just by appending batch to the path. And finally, you can make your API unbelievably flexible by supporting pagination, sorting, and filtering right there in the URL query string. Following these practices pretty much guarantees a robust, super developer-friendly interface.
Section 3. The power of idempotency. Designing for failure.
So we have a beautifully clean API design. But what happens when the internet just blips? Or a request accidentally gets sent twice? That brings us to idempotency. It's a bit of a mouthful, but the crucial takeaway here is that it guarantees retrying an operation will not lead to multiple executions. It will not change the state of the resource beyond that very first request. Essentially, it means safety during retries. If a client isn't sure if the request actually went through and they hit send again, idempotency ensures your system doesn't duplicate the action.
To put that into perspective, let's think about some real-world applications. Payment processing is arguably the most vital.
Think about it. If a network issue causes a gateway to retry a transaction, idempotency guarantees the customer is only charged once. It prevents those disastrous double charges. It's equally crucial in order management, ensuring only one order is actually placed. And in user account management, retrying a registration shouldn't suddenly spawn 3 identical accounts. Idempotent design, whether you achieve it through HTTP methods like put and delete or by generating unique processing IDs, is an absolute non-negotiable requirement for reliable systems.
Section 4. Scaling with microservice architecture, breaking things down.
Okay, so what happens when that single server we started with just can't cut it anymore? When our API suddenly has to serve millions of users, we have to start breaking things down into a microservice architecture. And the essential rules here are pretty strict. First up, single responsibility. A good microservice shouldn't juggle multiple jobs, it needs to do one thing perfectly. Second, treat your servers as stateless. Any server should be able to handle any request without relying on some locally saved context. Third, separate your data stores. Data should be owned and managed by the individual services to prevent a tangled mess of tight coupling. And finally, stick to lightweight communication protocols like REST or gRPC so all these little services can talk to each other rapidly.
If we expand those rules into best practices, there are a few advanced concepts you really need to keep in mind. Take deploying into containers, for instance. Tools like Docker isolate your services, which makes them perfectly consistent no matter what environment they're running in. Then there's domain-driven design, which is critical for properly organizing really complex business logic. And of course, orchestrating all these microservices. Using a master tool like Kubernetes helps you manage the massive chaotic complexity of scaling, discovering, and deploying all these tiny independent pieces as one cohesive application. It's like conducting an orchestra.
Section 5. Security and abstraction layers, protecting the core.
As our system evolves into this sprawling web of microservices, we have to figure out how to expose all that awesome power to the outside world while keeping the core locked down and secure. Security at this scale relies heavily on standardized frameworks like the OAuth 2.0 flow. What's so brilliant about OAuth is that it allows different systems to securely interact on behalf of a user without ever sharing sensitive passwords. Instead, an identity provider validates the user and issues an authorization token. The user simply hands that token to your server to gain access. It's secure, it's scooped, and it keeps your backend completely insulated from handling raw user credentials.
But beyond authentication, we really protect our core by designing at least 2 distinct layers of APIs, internal and external. Remember that quote about abstraction from the beginning? This is exactly how we prevent leaky abstractions. Your internal API is a flexible sandbox. It exposes all the features for your internal microservices to use, and you can tweak it without worrying about breaking some third-party app. Your external API, however, is a highly curated subset of those features. It is strictly exposed to users and designed heavily around backward compatibility. This separation of concerns is absolutely vital if you want to maintain your sanity over the long term.
And here is one final, incredibly practical tip for your external consumers. Don't just hand them a bare API. Seriously consider building a client library or an SDK. Whether it's for external users or just your own internal teammates, wrapping your API in a dedicated SDK drastically lowers the barrier to entry. It completely smooths out the debugging process, it speeds up their experiments, and it allows you to natively bake in your own best practices, like recommended retries and automatic timeouts, right into the code they're actually using.
And just like that, we have reached the end of our architectural blueprint. We've gone from the raw simplicity of a single server, navigated the tricky choices of REST versus GraphQL, built in idempotency for absolute safety, scaled everything out with microservices, and wrapped the whole shebang up with secure abstraction layers. So I want to leave you with this final thought to ponder. When you are consuming or providing services, which do you naturally find yourself gravitating towards? Bare APIs or robust SDKs? Every implementation has a unique story. What's yours?